structure of the kidney. We actually got to see some kidneys in the lab on Monday and Tuesday. We noticed they're kind of simple for as important a job, which they have, but they're built for their basic function of filtration. And so we looked at what made made the nephron unique is that it has not just one, but two sets of capillary beds. Noting we talked about the glomerular capillaries, whose job is to actually form the filtrate, and then contrasting that to the peritubular capillaries, whose job is just to have a role in reabsorption and secretion with the filtrate in the tubes. We also became introduced to the glomerulus, why it's unique, in that it has an arteriole taking blood to it, which we're okay with, but something new is something called an efferent arteriole, where blood actually is carried away from the glomerulus and then leads to that second capillary bed. And so the relationship of this afferent and efferent arteriole is really critical to the functioning of the glomerular capillaries, and so we'll talk about that a little bit more. This is an image just to visually illustrate for you. Again, our glomeruli, our nephrons, are in three-dimensional arrangement in our kidneys. So you can't always look at it and say left side, right side, whatever. You really got to kind of analyze the structure. And to differentiate the afferent versus the efferent arteriole, what we're going to add to today is the afferent arteriole tends to have a little bit larger diameter than the efferent arteriole. We'll talk about that function in just a minute. But also, the efferent arteriole is the arteriole that leads to the peritubular capillaries. Okay, so that can help you differentiate between the two so we can know the function of each. We're also going to add in a moment that the loops, those descending and the ascending limbs of our nephrons, are not the same length. Okay, so they'll have a slightly different structure for a slightly different function. Okay. The reason we have these afferent and efferent arterioles is to make sure the blood pressure is really high in the glomerulus, because we want to do only what at the glomerulus? Filter only. And so the way that the afferent and efferent arterioles are set up, it ensures filtration only, yet no reabsorption at the glomerular capillaries. So the arterioles are going to give a lot of resistance, and they're going to cause a high pressure inside of the glomerulus. We also just noted in the previous image that the afferent arterioles have a larger diameter when compared to what? I said larger than the efferent arterioles. And we'll clarify that in the next bit when it talks about vascular resistance. And so at the glomerular capillaries, we're going to just basically have filtration throughout the entire length of the glomerulus. So fluids, solutes, anything that's permeable to the pores of the capillaries, high pressure, is going to force the solutes and fluids out of the glomerulus into, eventually, the Bowman's capsule. And so the reason we have that different diameter of the arterioles is to ensure this filtration process at the glomerulars. So the afferent arterioles, we'll mention them now, we'll come back and better clarify them, but these are going to be a protective mechanism, if you will, for the glomerulus to ensure that it's not damaged by changes in our overall blood pressure. The efferent arteriole, its job, having the lower diameter, is to just, as I mentioned a moment ago, to make sure the blood pressure is really high in the glomerulus capillaries. Okay, so this is just redundant. The whole point is to make sure the glomerulus does not do what? So it doesn't reabsorb. Okay. Am I out of order a little bit? Yeah, sorry about that. Presentation-wise, it flows, but I'm sorry it doesn't work on the handout. So if we look at the anatomy of the different nephrons, as I mentioned a moment ago as well in the same image, that not all the loops have the same length. Some are longer, some are shorter. The ones that have a shorter loop in Henle are called cortical nephrons because they're closer to the cortex. Okay, and these are the most abundant of the nephrons. Okay, so like 80 to 85% of the nephrons are these shorter cortical nephrons. The juxtamedullary nephrons are the ones that are longer, and they traverse down into the medulla of the nephron, or of the kidney itself. So they're just a little bit longer. They go more into the medulla of the kidney itself. And the primary role of the juxtamedullary nephrons is to actually establish that solute concentration gradient in the interstitial fluid. If you remember, I think it was yesterday, we talked about how within the interstitial fluid, from the cortex to the medulla, the interstitial fluid goes from more dilute and becomes more concentrated. And we had a gradient, and we illustrated that's to keep the fluid flowing through the nephron. Okay, and so it's the juxtamedullary nephrons, these long ones, that actually establish that gradient, or is described here, this osmotic gradient, to keep the fluid flowing from the cortex area down to the medulla and then back up towards the cortex area. Either way, whether you're looking at a juxtamedullary or a cortical nephron, both will produce filtrate and thusly eventually urine as well. And this is a simplified image contrasting the cortical versus the juxtamedullary nephron. The difference is just the length of that loop. And so the longer ones help us make sure that this deeper area, more towards the medulla, has a higher concentration of solutes surrounding it. We look in a little bit more detail around the glomerulus. There's a structure called the Juxtaglomerular Apparatus. This is another one of those words that might cause you to panic a little bit when you first hear it, but if you walk through it slowly, and backwards if you will, so an apparatus is something, right, the thing, and it's juxta. What does that mean, juxta? Maybe you used it in like literature or your English classes, talking about juxtapositioning. It's, I think I've heard that. Juxta, adjacent or next to, okay. So it's the apparatus next to the glomerulus, okay. There's some specialized cells next to the glomerulus to regulate the glomerulus, okay. And the juxtaglomerular cells are adjacent to the afferent arterial vessels. And so there's just basically some smooth muscle cells and cells that also have the ability to release this thing called renin that we've kind of seen throughout the semester. And one primary job, besides releasing renin, is to serve as mechanoreceptors, receptors that respond to what? Mechanical changes. So basically, change in flow of the blood through the arteriole. They're kind of like stretch receptors, if you will. Okay. Tells us if the arteriole is really stretched or not. Again, it has a set point range of stretchiness for the afferent arteriole. So it acts as mechanoreceptors to what? What's this abbreviation? The blood pressure. We really don't want to have fluctuating blood pressure in the kidney because it will mess up our filtration. So we have this kind of intrinsic ability to monitor the flow using these juxtaglomerular apparatus cells. This image is probably a lot nicer image to really understand the structure of the nephron. I can see our arterioles. Which one is this? The afferent. This one's the efferent. Without reading the labels, you knew this because it's larger in diameter. Also, if you look in the juxtaglomerular apparatus around these glomerulus, you can see there's more smooth muscle cells. So we really want to be responsive to the blood flow coming in. And so the juxtaglomerular apparatus are these cells around here, and these first cells that we were talking about right around the afferent arteriole respond if that vessel stretches more with high blood pressure or recoils more with lower blood pressure. Okay? Those will drain. The afferent arteriole will take blood to the glomerular capillaries, and any blood will exit out via the efferent arteriole. We also have some renin-secreting cells in there as well, which we'll conclude today's presentation with. Be okay if I use the word juxtaglomerular now versus, say, 2 minutes ago? Just cells right around the afferent arterial to monitor blood pressure and then also secrete the stuff called renin. We've already identified between lab and lecture yesterday that there's a difference between filtrate and urine. We said filtrate is just modified what? It's basically modified blood plasma, with the notable exception, okay, there better not be any proteins, there better not be large red blood cells being forced out of the filtrate. Conversely, urine is that filtrate that's even more modified, and it's going to be more concentrated in true waste products or excessive products, and it's going to be stored in the bladder. You now know from lab Monday and Tuesday that once in the bladder, the bladder's an organ, so white blood cells and whatever else can kind of get in there, right? And then be stored in with the urine, but it's not added during the filtration process. So we're definitely familiar with the difference between the term blood plasma versus filtrate versus urine. And we've already gone through the phases of urine formation, so hopefully this is a review. It's starting to kind of fall together for you. We saw the animation, we did the pre-lab homework, and we did the handout number 7, looking at the 3 major phases of urine formation. And we said the first phase is filtration at the glomerular capillaries. We said any filtrate that is made may also be reabsorbed from the tubes back into the what? Very good, the peritubular capillaries. And as well, products, if they're reabsorbed, they actually may be what? The next phase would be secretion, right? From the interstitial fluid or from the peritubular capillaries back into the filtrate. And at that point, if there's no more modification, we have now formed urine. This is from your handout, number 7, which you turned in yesterday and should have received today, so figure 18.7. Summarizing the major phases of the urine formation. And you can kind of see anatomically where these processes happen. Filtration, we're going to add in just a minute, is based upon a pressure gradient. So this pressure gradient is going to force liquid from the capillary towards the Bowman's capsule. Reabsorption and secretion are going to rely upon our familiar processes based upon molecule solubility, and therefore if there's transporters or gradients and all those other factors which play in there, is going to dictate whether or not something is reabsorbed or secreted back into the filtrate. And the term for actually eliminating it from the body is called excretion. And we would excrete the urine. Urine. We've already seen the video, so I'm going to kind of skip over this. And I'd actually need to remove this particular video. I didn't realize this it's a good video, and it was on YouTube. And so apparently somebody swiped it from a publisher, and the publisher caught them, and so they've actually removed this little video. So it's not good to steal others' work, right? Put your name on it. So they got caught, whoever they were. The publisher video was good. And so we're just going to review each of those phases. The first thing we know is called filtration. And the glomerular capillaries are kind of like other capillaries, but with a little more oomph. They're more efficient when compared to other capillaries in the body, so in the brain or skin or whatever, because the area for filtration is actually more permeable when contrasted to any other old capillary in the body. We know the blood pressure is higher in the glomerular capillaries than other capillaries because of the afferent-efferent arterial relationship. Because again, we only want to do what? Here, we only want to filter. We don't want to reabsorb. And so because the pressure is higher, the net pressure is higher, and we know that our proteins, even though the glomerular capillaries are more permeable, they're still not permeable to large proteins because we don't have an ability to reabsorb them at the kidney itself. And so the question is, well, then what the heck is a filtration membrane? And it's a structure of a collection of cells that increase the surface area for filtration at the glomerular capillaries, while kind of, if you will, stabilizing the capillaries, because they are such high pressure, you don't want them to bust. Okay, so we have these cells kind of associated with the glomerular capillaries to help increase filtration area as well as increase stability. So probably the image is going to help a little bit better. You can see the glomerular capillaries in the red, and then the filtration membrane is due to these little cells lining the glomerular capillaries. And if you look closely at the cells, you notice how they kind of branch, and notice the area for filtration kind of looks like a maze. It actually increases the surface area for filtration if you look at it at a closer area. So we've got some stability, but we still have a lot of permeability for forcing substances, blood plasma out into the captured by the Bowman's capsule. Okay, so it's much more permeable than other capillaries in the body. To look at the function of the kidneys, a doctor would analyze one's glomerular filtration rate, or what you can call the GFR. And this quantitates how much filtrate is formed over a period of time, and generally you'll look at it per minute. And if we're trying to look at the filtration rate, just like anything else in the body, there's things that's going to influence that rate of filtration. The first is going to be the what? What is that abbreviation? The surface area. Obviously, the greater the surface area, the filtration rate will go which way? Up. The permeability of the membrane. If it's more permeable, the filtration rate should also go up. We'll kind of address that as well. And then including what's called the net filtration pressure, which we haven't really addressed this in any other capillary, so it might be a little bit new to us. And so we're going to look at the net filtration pressure. If we look at the filtration rate, it's actually most dependent upon the pressure gradient, which makes, we've seen that before. Pressure gradient is going to influence the movement of something as well. The pressure gradient across the glomerular capillaries is going to influence the filtration rate at the glomerular capillaries. And so if someone's filtration rate at the kidneys changes, it's probably due to a change in blood pressure. Okay, the primary influence on your kidney filtration is your blood pressure within the kidney. There are many factors which influence the filtration rate and the net filtration pressure. Your textbook actually quantitates many of these factors, and I can hopefully kind of oversimplify it for you. We learned that the afferent arteriole has a large diameter. The efferent arteriole has a smaller diameter. That kind of creates a traffic jam, if you will, a blood pressure traffic jam. Okay, so you got a lot of blood entering, but it's exiting at a slower rate. So there's a buildup at the capillaries, which is good because the capillaries are porous. Okay, so the escape route is not necessarily the efferent arteriole. Right? Some substances will escape, if you will, be filtered out. Okay. Now, at any other capillary, we learned if we add fluid to the other side, if you will, that causes pressure. So we have high pressure pushing substances out, but we have a physical pressure opposing the capillaries. So the outward pressure has to overcome that inward reverse. In addition to just the inward pressure of that fluid that just got filtered out, we're separating liquid from proteins and cells. We're also creating an osmotic gradient. So by just natural osmosis, this high concentration of water wants to go back where? It wants to go where? It goes to the lower gradient where there's less of it in the glomerulus. Okay? And so the glomerulus has a high pressure, is trying to push stuff out, but the filtrate wants to come back in. Pressure-wise and osmotic, like water attraction-wise, it wants to come back in. And so the glomerular capillaries has to overcome those two inward pressures and have a huge pressure forcing substances out. If you look at just a sample filtration, the glomerular capillary pressure outward pressure is about 16 millimeters of mercury, which may not seem much to you, but if you contrast that to another capillary in the body, it's about 2 millimeters mercury pressure. Any other capillary in the body, about 2 millimeters of mercury is enough to cause filtration, but then it reverses and causes reabsorption. 8-fold is the pressure at the glomerular capillaries. You can see that big difference. And this again quantitates why our glomerular capillaries can filter only, yet not reabsorb. And if we try to quantitate the blood flow to the kidneys receive about 625 mils of blood a minute. And if we look at the net filtration rate, your kidneys can filter upwards of 200 liters of blood a day. We know that we don't have that much blood, but if you contrast that to any other tissue in the body that's not a reconditioning organ like the kidney, they receive about 3 liters of blood. So 3/4 to half of your blood per day, when the kidneys themselves are receiving folds difference. And it's due to that pressure gradient, which is established at the glomerular capillaries. Okay. So just like anything else in your body, the filtration rate needs to be at set point. And these 2 points will tie into your pre-lab that you turn in Monday and Tuesday. If the glomerular filtration rate is too high, the pressure is too high, and the filtrate's being forced out too quickly, and it's just zipping through those tubes, what's not going to happen well? Reabsorption is not going to happen well. Okay? And so substances that would normally be reabsorbed, like, say, glucose, sodium, water, they're not reabsorbed, they're not kept in your blood, and they're where? Where do they go? If they're not reabsorbed, they go where? In the urine. They're wasted. Okay? Which it doesn't make sense to spend your energy, say, for example, releasing glucose for your cells to use, and you just pee it out, if you will. It's wasteful and damaging. Conversely, if your filtration rate is too low, so maybe it's cut down by half, what do you think happens? Everything can be reabsorbed, whether it's good or what? Bad. Okay? And so what happens is you can reabsorb toxic products, excessive products, whatever the case may be. And your blood concentration falls out of set point, and it's just that cascade effect of disease, basically. And so your body's going to have to make sure that filtration rate is adequate. Okay. And the way that your body can ensure the filtration rate is adequate is by some type of control mechanism. And the kidneys also have an ability to intrinsically control themselves, and of course they can be extrinsically regulated. The term for the intrinsic regulation is called renal autoregulation, so it controls itself. And extrinsically, we know the nervous system can control it, and we also know the endocrine system can control it. The difference will be short-term versus more prolonged control over the kidney. Which do you think is the fastest of the 3? Hunch is neural, but there's one even more fast. Autoregulation. Kidney's right there. It can monitor itself. Nervous system's fast. The kidney itself, the mechanisms are right there. The sensors and the control are right there. So it's even more fast than the nervous system. Are we okay to move on? All right, so if we look at the intrinsic controls, basically it's going to be dependent upon that juxtaglomerular apparatus. We talked about the smooth muscle mechanosensing cells. That is the intrinsic mechanism that the kidneys use to monitor the pressure going to a particular glomerular. So there's 2 ways of monitoring it. Myogenic means what? Muscle. Okay. So it's those smooth muscles, which I just mentioned. They respond to changes in renal, this is cut off here, blood pressure. Okay. And so, like I illustrated earlier, the stretching of those smooth muscles indicates pressure is what? Probably high. And if they're kind of recoiling, the blood pressure is probably a little flow. And so by negative feedback, the kidney itself would try to fix the flow through the afferent arteriole. And then also flow, just velocity monitoring as well. So not just pressure, but also velocity, or described here as flow dependent through the Juxtaglomerular Apparatus. So the kidney can monitor the flow and the pressure of the blood through primarily the afferent arteriole, but also the efferent arteriole, using those juxtaglomerular cells. And they're going to work together, right? Obviously, if there's stretching, the blood flow is faster. If there's recoiling, the blood flow is lesser. So they're certainly interdependent upon one another. Extrinsically, typically, the nervous system, when the parasympathetic nervous system is prevailing, the kidney is regulating itself. However, when your fight or flight system becomes activated, your sympathetic nervous system is altered. Okay, so when you're so this is, let me restate this. This is when the sympathetic nervous system is at rest, or maybe a better way to say that is when what? When the parasympathetic nervous system is prevailing. So when you're resting and digesting, the renal autoregulation, intrinsic mechanism prevails. However, when you go into that fight or flight system, your epinephrine, norepinephrine from the sympathetic nervous system actually causes the afferent arterioles to constrict. And then the filtration goes which way? Down. Because we need to distribute the blood not to the kidneys so much at this point, but more to your skeletal muscles, to the liver, the respiratory system, or whatever organs are being activated during your time of excitation. Which makes sense, right? When you're excited, you know that your urine output should go down, because the kidneys, although receiving blood flow, not receiving as much as if you're just kind of monitoring and kind of keeping everything status quo. So that's a quick change in blood vessel arterial diameter. The Renin-Angiotensin mechanism is this more indirect hormonal pathway to alter blood pressure. So for now we're looking at, well, what if there's a problem with the blood pressure and it prevails? And we're going to end up with the release of renin from the juxtaglomerular apparatus. Okay? And so what happens is there's this molecule called angiotensinogen. It's a protein. It's circulating in your blood. So it's a soluble protein. It's circulating in your blood, but it's considered to be inactivated. Does that word make sense? It's there, but it's not activated. Okay? So it can be activated. When our blood pressure changes, the juxtaglomerular apparatus can release this product called renin. And renin will activate angiotensinogen to an intermediate called angiotensin 1. Okay, so this is starting a cascade. Angiotensin 1 is also a precursor that can be converted by an enzyme called angiotensin converting enzyme. Okay? It converts it from form 1 to just angiotensin. You may recall angiotensin from our chapter 14 discussion, in that it's going to target the release of our two hormones, which are hormones, aldosterone and also what? And eventually antidiuretic hormones. So let's add this in here. What page are we on? We're going to add in here and antidiuretic hormone from the very good, from the posterior pituitary. Okay? What happens is our overall blood pressure is actually going to elevate because of the effects of aldosterone, antidiuretic hormone, and some other pathways as well. This pathway we saw at the end of chapter 14, if you need to make a reference to it. We saw this on page 8 of your chapter 14. We've actually seen this pathway on page 8 of your chapter 14 notes. The next image that I have for you, coming up in just a minute, just adds the organs, like gets pictures of the organs. We know that aldosterone from the adrenal cortex, once it's triggered for release, will target our tubes of our kidneys to promote sodium what? Reabsorption. When we reabsorb sodium, a gradient is established for other particles, including chloride ion, and then also an osmotic gradient for water. So the net effect of aldosterone is to target the kidneys for sodium reabsorption, but ultimately water reabsorption. And we know through this Unit 4 material that when water is reabsorbed, it's not going into the urine, so our blood volume remains what? Higher. Okay, and so our blood pressure will remain higher. Right, as summarized there. It says, as a result, okay, both our systemic and our blood pressures elevate. Okay, so you'll see this pathway activated if your systemic blood pressure is low for a period of time that the sympathetic nervous system can't alleviate. So we'll turn this on. If your blood pressure is too high, should we see this pathway activated? In my blood pressure is, I've got a family history and I eat salt and french fries and coffee and stuff. Will I see this pathway activated? No. It's actually inhibited to hopefully bring our blood pressure back down to the set point. So this pathway is activated when our blood pressure is low for a prolonged period of time. Again, on page 4, you can see the pathway. Angiotensinogen, that precursor, is manufactured by the liver and just circulating your blood in the inactive form. When our blood pressure drops, that Juxtaglomerular Apparatus detects that and releases renin. Renin is added to the circulatory system and it catalyzes angiotensinogen conversion to angiotensin 1. Okay? This is, we said, an intermediate angiotensin converting enzyme. You can see is actually produced by our lungs. Okay? Converts it to angiotensin 2, which we had multiple targets. It can trigger the cortex to release aldosterone. It also targets the posterior pituitary to release, which is called antidiuretic hormone, ADH. So it targets the cortex to release aldosterone, targets the pituitary to release antidiuretic hormone. It also causes some of our blood vessels to constrict, and that increases resistance, which increases pressure directly. Indirectly, aldosterone to kidneys promotes sodium reabsorption, then chloride, then water, which brings our blood volume up. Antidiuretic hormone also targets the kidneys to promote directly water reabsorption, which brings our blood volume up and our blood pressure up. Okay. Something else really interesting about the angiotensin molecule, it acts on the hypothalamus to activate what's called the thirst mechanism. So whenever you feel thirsty, when you feel parched, you're actively seeking out something to drink, you probably have angiotensin 2 circulating through your blood, telling your hypothalamus, go find water. And so you take in water, your blood volume goes up. Okay, and hopefully you're diluting out your solutes. So again, another hormonal, some of the pathways which we've actually seen, but in effect here at the kidneys to bring our blood pressure back up, to bring our filtration back up at a set point in this pathway. What questions do you have about this pathway? Those hormones you've seen, and we've seen the blood pressure as well in unit, so we saw the hormones in unit 3, and blood pressure regulation as well in the start of unit 4. All right, so we talked about filtration and everything which influences it, and we know that once filtration happens, substances can be reabsorbed, where products are added back into the peritubular capillary plasma. We already know that reabsorption can be active or passive, whatever, depending upon the solubility. Some substances can go through the pores, or described here as paracellular. Para means going between the cells. Essentially, all of your organic nutrients and that your body needs, okay, so your carbon-containing nutrients, your sugars, etc., they are going to be reabsorbed once they're filtered out. And we also know that this can also be under the influence of hormones. We'll kind of address that with aldosterone and anti-diuretic hormone. If we look at an example of sodium reabsorption at the kidney tubules, we're going to use our familiar friend, the sodium-potassium pump. Is actually going to promote this sodium reabsorption. So we actively reabsorb sodium to establish this secondary active transport of other molecules back into the circulatory system. Okay. So it's highlighted here. The bulk of our sodium reabsorption is just going to give energy, that gradient to reabsorb, you name it. Most everything is going to be reabsorbed by the secondary active transport after sodium is actively reabsorbed. So, as I mentioned just a minute ago, so water, other charged particles, lipid-soluble particles can be reabsorbed. And then, as I mentioned as well, secondary active transport is going to reabsorb some substances. Filtered out and then transport it back into the blood is basically what's happened. Does anybody remember from lab where the bulk of this reabsorption actually happens? Where's the physically in the tubes? Where's the bulk of the reabsorption taking place? Well, the capillaries take it up, but at the tubes themselves, what part of the tubes? The what? It's not even in the middle. The bulk there it happens along the way. We see the first starting and the high proportion of it happening where? First happens at the proximal convoluted tubule. It's just chock full of transporters. You're right, though. The loop does reabsorption as well. That's glucose carriers, etc., all sodium transporters right there. As soon as something filters out, we're boom, 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 picking it back up into the peritubular capillaries. So this image really just summarizes the active and primary and secondary active transport and also the passive transport of some substances to help kind of put it into perspective where we're at. This is a tube, the cells making up the tube, so say the proximal convoluted tubule. The other half of it's not even shown. Okay, so it's just looking at, they could have done a mirror image. Okay, this would be the lumen. The dark area would be the lumen of the tube. Excuse me. Thank you. The cells which make up the tubes are going to be, as I mentioned, full of the transporters. And then we can have an interstitial fluid and then a peritubular capillary, its cells, and the blood plasma, the lumen, in the lumen of the capillary. And so illustrating our familiar transporters, charged particles, we have pores basically between the lumen and the interstitial fluid. They just diffuse down their gradient. Anything that is lipid soluble is going to do what? It's just going to simply diffuse right down its concentration gradient. But we can also actively transport sodium out and the potassium in. So we also have our familiar little leaky ion channels playing in a role here. The key placement where we're going between reabsorption and secretion is where the transporters are located. Are they located facing the interstitial fluid, or are they located facing the plasma? That's really going to dictate whether something is kept or secreted, reabsorbed or secreted. And so here we can see sodium is going to be actively reabsorbed towards the interstitial fluid, and it would diffuse into the peritubular capillary, because there wouldn't be a channel letting it back in. Like we saw maybe in a nerve, there's no leaky sodium channel in the tube cell, and so we can take it into the capillaries. You may find this interesting, though. Urea is a what? Is what? It's actually it's lipid soluble. I mean, it comes from protein catabolism, so it wouldn't be a full protein. It's from the breakdown of proteins. It's lipid soluble, If we were to oversimplify it, what is it? What is it? What do you call urea? What's it? I don't call it anything. It's a waste. And look at it. It's a byproduct of protein catabolism, and it's a waste product. And look where it's moving. It's a waste, but it's being reabsorbed because it is fat soluble. This is why, or this is one reason why it's so important for our kidneys to work well, because things that are fat soluble and waste products are only removed at about 50%. Half is lost, half is reabsorbed because it's lipid soluble. We don't have a way to trap it. We can't get our protein. We can't trap it in the lumen. So even though it's a waste product, remember diffusion goes equilibrium, so they equally get lost or excreted and equally get reabsorbed because it's lipid soluble. All right, so if we look at reabsorbed substances, if there's a carrier, there's only a maximum amount of work which the carriers can do. It's called the transport maximum. And so most things that are going to be reabsorbed, there's going to be some form of carrier or transporter or a channel or something like that. And if the carrier is overloaded, it can only carry at a certain rate. So if there's more substances being filtered than there are carriers, those substances aren't reabsorbed. They're lost in the filtrate and lost in the urine. So things that are really critical to us, we should have plenty of carriers for adequate reabsorption. This isn't displaying well, but if you check out table 18.1, you'll be able to read it a little better from your textbook. And it illustrates some molecules that are filtered, yet the percentage of reabsorption. So if you look at things like water, it's filtered at a high proportion, right, it's in our plasma, and 99% of our water is actually reabsorbed, which makes sense. If you're filtering 200 liters of blood, you're not peeing 200 liters of blood, right, or urine. Okay, so it makes sense that we're reabsorbing it. Glucose is reabsorbed. Can y'all read this? How much? 100%, because we have plenty of glucose transporters across those proximal convoluted tubes. Urea, as I mentioned, although a waste product, it's reabsorbed at about 50%, even though it's a waste, because why? It's fat or lipid soluble, and we just can't keep it. We can't keep it in the tubes. Sodium, also reabsorbed, 99%. We've got the hormonal influence on that as well. Potassium, an important cation as well, reabsorbed less, okay? Because we're going to add during secretion. Remember, aldosterone actually promotes sodium secretion, so we'll get to that in just a second. Calcium, we talked about how important it is, how its reabsorption can be hormonally influenced, so we don't necessarily reabsorb 100% of calcium. Some of it's eliminated in the urine. Chloride ion, bicarbonate ion, also reabsorbed at high proportion. If we filter everything and reabsorb so much, why do we do this? If we filter something and then reabsorb things like glucose and water at nearly 100%, why do we even filter? If we're reabsorbing so much, why do this? Why filter and then reabsorb? The only ability to get rid of waste. And so we're selectively reabsorbing some substances. What's not shown is substances that are not reabsorbed, right, that are actually secreted out. And this is our only chance to get rid of excessive things. We're at that 0.8% of water. Okay, that's an ability to get rid of substances. If you never filtered, you would just indefinitely accumulate water and solutes and just be a big mixed, unregulated bag of just a mess, right? And so we've got to do this, even though we're reabsorbing. We also noted as well, not everything is reabsorbed. So something that's not going to be reabsorbed is something that does not have a carrier. If it's not lipid soluble, it's just physically too big to go through those pores between the capillary cells. Some examples, creatine, again, protein byproduct, uric acid. There are some examples of things why we're doing this, to get rid of those waste products. The next phase is secretion, which we've already addressed. And kinda is basically reabsorption in reverse, where products are moving from the peritubular capillaries or interstitial fluid back into the tubule content and added to the existing filtrate. And the whole point of secretion is to get rid of substances that may not have already been in the filtrate, get rid of those lipid-soluble byproducts, excessive cations like potassium, and then regulating our blood pH, right? If our blood pH is altered, we can get rid of whatever we have too much of, whether it's hydrogen ions if our blood is acidic, or bicarbonate ions if our blood is a little bit too alkaline. And this simple image from a previous textbook illustrates, again, the directionality. The yellow indicating the lumen of the tube, and beige the tubular cell, the blue the interstitial fluid, and the red the capillary, right, the peritubular capillaries. In secretion, particles will diffuse down the gradient. Here we can see the sodium-potassium transporter, but you notice the potassium leaky channel is now facing the lumen of the tube versus the interstitial fluid. So under hormonal influence, if we add more potassium channels, potassium is going to diffuse down this gradient where it was just pumped into, and it diffuses only towards the lumen of the tube, not back into the interstitial fluid and not back into the blood. So it's a regulated process of secretion. And so we already saw an example for potassium. Aldosterone from our adrenal cortex can regulate this process. If our blood potassium levels get too high, we can see more potassium secretion. And then if it's too low, we obviously would lessen the number of those potassium ion channels towards the tubes. Y'all with me so far a little bit? And we have a few more minutes, so we'll talk about how the concentration of the urine output can actually be influenced, and we know it can be hormonally influenced, so we'll just kind of fully address that. The Lupa-Henle, we talked about the descending limb of Lupa-Henle versus the ascending, not only the directionality, but the descending limb, if you recall from the animation yesterday, is where the bulk of our water reabsorption happens, and then contrasting that to the ascending limb, where it's more permeable to, and here it says solutes, but like sodium ion, where we can do our sodium reabsorption. Our collecting ducts as well can reabsorb a lot of urea down there as well. And so basically what we're going to do, if I take water from the filtrate and the urine becomes more what? Concentrated. If I take sodium out, the urine becomes more dilute. Okay, and that's what we're going to address here. I want to look at forming more, 18.2. Looking at secretion, proximal convoluted tubule. Just to reiterate the question I said, the proximal convoluted tubule does the bulk of our reabsorption, a little bit of secretion. Lupa-Henle, primarily reabsorbing water to make urine more. If I take water out, the urine becomes more concentrated. If we look at the ascending limb, reabsorbing sodium, and not really much secretion going on. In the distal convoluted tubule, still a little bit of reabsorption, but now a high proportion of secretion of potassium and hydrogen ions. And the collecting duct, too, as you remember from our animation yesterday, that still can have some reabsorption going on, but it's our last-ditch effort to secrete products as well. So if we want to change the, we've already seen that, if we want to change the concentration of the urine, we can influence the permeability of the descending and the ascending limb of the Lupa-Henle. descending where we're taking out. Get my directionality right, this is confusing. But the image will help me a little bit better. If we look at the, I'll come back to that slide. Anyway, our collecting ducts, if we're trying to make dilute urine, at this point, we don't want to reabsorb the water, basically. Okay? And so the water, we don't want to have additional transporters. We don't want to have that aldosterone antidiuretic hormone effect going on at the kidneys, at the nephrons themselves. And so we can reabsorb not the water, but take out solute particles, sodium and whatever else. Take it out, leave the water in, and the urine would become more dilute. If you leave the water in, the filtrate, and pick out sodium, about 50 milliosmoles doesn't make necessarily much sense unless you contrast that to more concentrated urine, so upwards of hundreds of milliosmoles of concentration compared to the dilute. So the image on page 7 of your handout will kind of hopefully illustrate this. If we're looking at the formation of dilute urine, we don't want to have so much as much water reabsorption in the dilute urine. So if you look at the numbers, okay, our filtrate coming from the proximal convoluted tubule, the concentration of the filtrate about 300 milliosmoles. At this point during the descending limb, we said it is permeable to water, so water can be reabsorbed. That effectively actually concentrates, increases the concentration. But in the ascending limb of loop and Henle, now we can pick out our solutes. And if we take out solutes, the concentration of the filtrate becomes more dilute. Okay? And at that point, just don't influence anymore, don't take any more water out, and it remains dilute. Conversely, if you look at that concentrated urine, our hormonal pathways that we're familiar with, antidiuretic hormone can influence this. So the antidiuretic hormone is circulating through the blood. We said about 99% of the water is actually reabsorbed, changing the concentration of the urine and the filtrates. The proper term or an alternative term to describe this is called facultative water reabsorption. It's being facilitated right under the influence of antidiuretic hormone. So with this, we add more aquaporins, more water reabsorption, and that as well, kind of summarized in an analogous picture there on page 7 of your handout. In this final scenario, we're looking at more concentrated urine. Starting out the same, the filtrate entering at about 300 milliosmoles. We're going to naturally just reabsorb water during that descending limb of loop of Henle. Okay, we're going to concentrate the urine. Still going to reabsorb sodium during the ascending limb of the loop of Henle, but then now the collecting ducts under the influence of antidiuretic hormone reabsorb water. It now causes the filtrate to become more concentrated, or the urine to become concentrated. And so it just depends on what's being added to or removed from the filtrate, dictating the concentration of the urine, or maybe what you may be more familiar with is it's more yellow, more stuff, or more clear, less stuff, more dilute. It's kind of what you might be more familiar with. And that actually concludes our semester material. That leaves us about 15 minutes to field any questions for our Unit 4 test tomorrow.